Hello, everybody. I'm Randy Stott. I am the managing editor of Gear Technology and Power Transmission Engineering magazines. I'd like to welcome you here today for our session of Ask the Expert Live. Today we're talking about gear design, and I've got some experts lined up to answer your questions. Please feel free to raise your hand at any time if you have a question you'd like to ask to the panel. Otherwise, I also have some questions that readers have sent in, and I will be asking them to keep things moving. But before we ask any questions, I'm going to turn it over to the experts so that they can introduce themselves. We'll start here with Professor Stahl.
Well, thank you for the introduction. My name is Carsten Stahl. I'm head of the Gear Research Center, the FZG, at the Technical University Munich. The FZG is doing research on gears since 1951 and is one of the largest gear research center in the German academia.
Greetings, I'm Frank Uherick. I'm principal engineer with the Rexnord Gear Group in Milwaukee. I've been in gear design since January 2nd, 1980. And I also have the honor and privilege of being the chairman of the AGMA Helical Gear Rating Committee.
Good morning, my name is Hartmut Müller. I'm Chief Technical Officer of the Klingenberg Group, and I'm working now 25 years in the area of gears, especially bevel gears.
Good morning, I'm Octave Labath. I'm a consultant presently. I haven't retired from a gear company after 39 years. I'm chairman of the AGMA Epicyclic Gearing Committee and have enjoyed gears for a long time. Thank you.
Thank you, gentlemen. I'm going to start off with one of the questions from our readers. So here we go. Is it true that ISO 6336 rates gears with a higher load capacity than AGMA 2101? Frank, go ahead.
That's an interesting question. The geometry that each standard is based on, whether it's ISO 6336 or AGMA 2001, is slightly different. So if you're designing a gear set to maximize your rating in AGMA, you probably won't maximize your rating in ISO 6336. In general, if you're looking at carburized, hardened, and ground product, if you have a coarse pitch, few numbers of teeth, 15, 16 teeth in the pinion, an AGMA rating will probably beat an ISO rating. If you are, on the other hand, looking at 26, 27 teeth in the pinion, you're probably going to get more flank rating or durability rating from the ISO set than you will for the AGMA.
I would like to add something here. I just stopped the ISO meeting, which I'm sitting in at the moment. So we are discussing here at a site of the expo the rating of the flank capacity of gears. And we are exactly discussing these differences between AGMA and ISO. So certainly they come from a different route, and they handle geometry and material and the influences differently. So there are differences. And if you try to peek into these differences, you will find them. Like the approach to calculate the bending stress is different. We have the 30-degree tangent and the parabola in the AGMA. There will be slightly differences, but for standard gears, they are very, very close. And we are trying to close the gaps even further by improving the calculation method for ISO and adding more factors and more influences into the calculation method.
You did say for standard gears, didn't you?
Yes.
There are some differences between ISO and AGMA when you have non-standard gears. A positive correction will give you a great increase, or a nice increase in strength in AGMA, and you might not get it in ISO. In fact, it might even go the other way.
Yes.
And there's a paper that I presented in 2011, and there's an article in Gear Technology that followed that. I suggest you look at it. Another thing you might want to think about is years ago when we looked at catalog ratings for ISO versus AGMA, the ISO ratings were always higher than the AGMA ratings. Now, these are standard catalog units that probably weren't ground tooth, they weren't carburized and hardened.
Very good. Thank you, gentlemen. Next question is, most gear software requires that you know the gear geometry before you can calculate load capacity. Is there any software that will design a gear set from the application data?
So maybe I start with it, with the answer. In Germany, there's a German Research Association for Powertrain, which consists of more than 200 members, and they fund a lot of research work. And out of this funding, we developed a software which is available for the members, which is called GAP, Gear Design Program, which is capable of doing that. So the number of stages, and then the number of teeth, the business and material proposals, which is based on the Niemann-Winter approach.
This is slightly different for bevel gears, since bevel gears have always to be calculated as a pair. And the interesting thing of bevel gears is that you need to know something of the environment. You need to know the deflections, the load cause deflections, and then you can optimize your gear set. There are influences like the tool diameter, there are influences of spiral bevel, all these things, spiral angle, all these things, and up to now there is no automatic solution which will create a spiral bevel gear set which is optimized for a specific application. You always need to have an engineer sitting behind the keyboard.
Many years ago, Bob Arichello was selling a software program that was called GearCalc. It would select geometry for a gear set if you put in the speeds and torques. That program is no longer available, but there may be a version of it at the KISSSoft library.
And for those of you who are not computer savvy, there is an AGMA information sheet called Recommended Design Practices for Minimum Weight Gear Design, which outlines, I think, Bob Arichello's method in a document, which you can also use to come up with that initial estimate of gear sizing.
That standard was almost written by Bob himself.
Can I ask why is Bob's program no longer available?
Well, number one, it was written years ago and runs in MS-DOS.
So it was never updated to run in current environments, but would it be still applicable today?
If you had a copy of that program, you could still use it in an older machine. I don't know whether it run on a brand new PC or not, but I have it running on my PC at home.
I have a copy of it from KISSSoft.
Oh, you do?
It is available. You best contact Bob directly, and he has an approval from KISSSoft to sell it apart from the KISSSoft package.
Thank you. Anybody who has a question in the audience, just raise your hand. But for now, I'm going to move on to the next reader question. What is the maximum allowable pitch line velocity for spur gears?
Well, it's difficult to answer this question. Basically, as long as the lubrication works, you can run as fast as you want until the lubrication will stop working, and then you have immediately scoring. Another thing which we would like to stress is it also depends on the type of lubrication. If you have splash lubrication, once in a while all the oil will be on the gearbox and no more on the teeth. So you need to have injection lubrication or better a spray lubrication. We designed one high-speed gear set which works about 30,000 RPM. It's a spiral bevel gear set, and we drilled holes into the root area. We had a hollow shaft, and we just blow in oil mist. And this works perfectly, and we could minimize the loss of the splashing losses because there is no oil in the gearbox. But to answer this question, it depends on the lubrication.
The other item that you also have to worry about is the tooth quality. If you have a gear traveling at those speeds, and high pitch line velocity is probably 30,000 feet per minute and higher, you've got to get accuracy. If you've got pitch or spacing errors, you're going to have massive vibration. It's just not going to work. To the point made earlier, you also don't want to dip that gear. If your gear is going much over 2,400 feet per minute pitch line velocity, you don't want it traveling through an oil bath. You want to get the gear, maybe dip it an inch, or maybe dry sump it, which means don't have the gear contact oil at all, and spray the gear with jet lubrication. The third thing you need to worry about is balancing. Again, when you're in those types of high-speed applications, 30,000 RPM, 40,000 RPM, you also start to need to worry about critical speeds when you have a vibration issue and the gear set excites a natural frequency of the shaft. And if you're not careful and you happen to be running at a natural frequency of the shaft, you can get a surprise. And a surprise is defined as the gear exiting the housing at a high rate of speed, blowing out of your test stand, through the roof, and into the parking lot. And I see a couple of people are chuckling over that. Been there, done that. So, and the other question I would have in terms of looking at maximum speed of a spur gear, it's probably also going to be noisy, because you're going to get 100% tooth contact. You come out of mesh with one tooth and boom, you load the next tooth totally across the face. Gearing is more double helical, where you can get more than a tooth in contact, hopefully two teeth in contact, and control your noise and vibration that way.
When you're doing high-speed spur gears, you might look at high contact ratio gearing. And when you're operating in these speeds, you need a good gear. And you might also want to silver plate those teeth.
I would like to add another thing. Manufacturing and running a gear is one thing, but calculating the load limit is a very important thing too. And the standard calculation methods do have an area of applicability. And for example, the micropitting calculation method is limited to 60 meters per second. If you exceed that by far, the method may not be applicable. So you must be aware in detail what the lubrication conditions are, whether your calculation methods are applicable or not.
Very good. Thank you, gentlemen. Question from the audience.
Frank, does that mean that if you are pushing it, you've got to be very sensitive where you park your car? Is that is that what you're trying to tell people?
Car parking is important in gear design. Fortunately, I usually get to be the first one in the plant in the morning, so I have my choice of over 600 parking spaces. But basically what that means is you really need to do a lateral critical speed analysis. And you're not only looking at your gear geometry, but also your shaft geometry, your bearing type. You're using a sleeve type bearing or a tilting pad bearing, and try to make sure you can design away from a critical speed. Typically, you want to be at least 20% away from there. You can run through a critical speed, but don't hang around there. Just get through it, get over it, and the box will run fine. And park far away.
Take the people mover.
All good advice. Next question is, how do you select the number of pinion teeth for helical gears?
That's an interesting question. As mentioned earlier, there's an information sheet, the rational design of gearing, that tries to balance basically 4 parameters when it comes to gear design. When you're trying to optimize a gear set, you're worried about pitting, you're worried about bending or strength, you're worried about scuffing and scoring, and you're worried about micro-pitting. Wear plays a role in that. It depends on what you're doing. If you're looking at a rock crusher, for example, you want high strength. You want a tooth as large as possible, so you're going to tend to move toward a fewer number of teeth, 15 teeth, 16 teeth. If you're looking at a generator drive that's going in at 1800 RPM and it's in a residential area, you may be sitting in the 18, 19 teeth. You may be over 20. If you're trying to get a lot of teeth in contact, you want to go to fine pitch, large numbers of teeth. Of course, there's no free lunch. The more teeth you throw on, the strength rating goes down. So I think a lot of it depends on where your critical design parameter is. If you're looking at scuffing or scoring, you're going to be in 26 teeth and above. If you're looking as an increaser, the rules that I use are somewhere in the 30 tooth range. But again, it depends on what do you want that gear set to do. And it also depends on what rating standard you're going to use. Because as we said earlier, if you tend to be coarse pitch and carburized, 25-degree pressure angle, AGMA may be beating ISO. And I would turn to my colleagues here to comment otherwise.
I completely agree. It depends on what you're looking for, and then you optimize according to the calculation which you trust. I would like to add another aspect. The number of teeth has something to do with the mesh frequency, and you can match mesh frequency to the resonance. So if you have an unlucky condition where the mesh frequency lies close to or exactly on the resonance, you can juggle around a little bit with the number of teeth and go away from that. So normally for high-speed gears, it's good to be below the mesh resonance. You choose a low number of teeth.
I'd like to comment on, Frank mentioned scuffing and scoring. Scoring is a term that is no longer recognized in the AGMA nomenclature committee. They only use scuffing. Scoring is something you did after a football game.
You can't calculate that.
Okay, gentlemen, next question is, how do you select the profile shift for the pinion for spur gears?
I would say that, number one, you want to select a profile shift that gives you a gear that doesn't have undercut, number one, if you're working with lower numbers of teeth. And number two, most people will make the pinion have a positive profile because they can make the gear have a negative profile and the gear teeth will balance out.
The other thing that you want to look at is, again, what are you designing for? If you're in a strength situation, you may want to balance strength rating between pinion and gear. In the old days, before 1980, AGMA did not have a life factor to adjust their ratings. So people would tend to always make pinions stronger than gears. You want to make the pinion tooth larger. And go from that standpoint, you want to balance the J factor, which is the AGMA geometry factor. You have to watch your heat treat with that because probably your pinion is harder than your gear. So you've got to not only balance J, you've also got to balance the strength rating. So that would be another criteria to look at when you're selecting profile shift.
I would like to add, it's a very generic question. So the profile factor is a general adjustment factor. You can adjust according to the demands of the gear, which is strings, bending, and on the flank, and also the efficiency. So you can adjust the speed, velocities on the tooth flank. And you can adjust to the tools you have in your workshop. So if you have only a couple of tools, you can also play around with the profile shift factor to adjust that you can get a gear with acceptable or no undercut if you have no adequate tools. So there is no specific answer possible. It's one of the 5 or 6 play factors to adjust to the optimal gear.
Let me try to give a simple answer to this very general question. What we always recommend is that the profile shift should be selected in such a way that you have a balanced specific sliding. And if you still have undercut, then you need to move a little bit with the profile shift as a very first simple rule. But I don't want to criticize in any way what you said. I fully agree. But just as a starting point, balanced specific sliding.
You can balance the specific sliding for almost any profile shift you select for the pinion, but you're going to have a matching or a compatible profile shift on the gear and maybe change your center distance.
That's right.
Thank you, gentlemen. Next question is, can you explain the types of mismatch on bevel gears or crowning on cylindrical gears that gears can have? It's a broad question and maybe requires an in-depth answer. Hartmut?
Okay. Well, mismatch. A bevel gear set always has to have a certain amount of crownings because it's a three-dimensional gearing. This is different from cylindricals. If you change the axis distance in an involute gearing, nothing will happen in the contact conditions. But this is completely different in bevel gears. Therefore, you need to have a crowning. And there are basically 5 parameters to describe this crowning. This is more or less arbitrary. It's a definition. You don't need to understand it. You just need to get used to it. This one is the lengthwise crowning. Next is the profile crowning in the tooth height direction. Then we have a spiral angle difference. This means, do we have the contact more to the toe or more to the heel? Then we have a pressure angle difference. This is top tip root. And then we have a longitudinal twist, which defines the bias conditions. And with these 5 parameters, you can easily start designing a bevel gear. But it's a big but. Everybody that talks about flank form modifications, in many cases, these are nice conference talks. A very clear statement from my side is, as long as you don't know the load-induced deflections, you can make a lot of fancy papers this done. In the background, we have the calculation of the machine settings, and if you have a theoretical machine, you would create exactly this flank. This is totally different in cylindrical gears. In cylindrical gears, you have a function-orientated flank form modification. It's purely on the function, and you don't care about the machinability. For example, if you make something in profile crowning, you have different parameters to optimize a flank form than you do it in generating grinding. And for the function-orientated flank form modifications, most of the gear engineers don't take into account the way how this gear will be produced afterwards. And if you take the readings on an inspection machine, you always have both. You have the theoretical difference in between a machinable flank form and the function-oriented flank form, plus the deviations in manufacturing. And you need to have an experienced guy reading this chart, and then he can do it.
One of the other things to keep in mind is, when should you crown a pinion? And typically, the rule of thumb that I always use are square pinions or happy pinions. In other words, the pitch diameter of the pinion is equal to the face width. Now, that probably doesn't work on a 1-to-1 ratio, but on a 3-to-1 ratio, a 4-to-1 ratio, that works very well. A lot of designers will come in and say, I need a 6-to-1 reduction, and I'm not just getting the rating I want, so I just keep widening the face and widening the face, and yeah, I finally have got it. And they have a pinion that has a 5-inch diameter with 10 inches of face. What they really have is a 5-inch diameter pinion with 5 inches of face being used, and the other 2.5 inches on either side is just sitting there going along for the ride holding oil. So crowning can address some of that. I mean, a lot of people will come in and they'll use advanced topological software, numerous items in the marketplace to try to recover a bad design decision, which is the face width's too wide. Don't put all that ratio in that single stage. So you want to not only look at what is the orientation of the size, but also, and was mentioned before, the loading. If you design an industrial gearbox and you don't know where it's going, you have to sort of guess at what the load is, and you make your best shot at crowning. One of the great challenges in wind turbine gear design is you never know what the loads are, yet you have to pick one load to work out all the crowning. And that becomes the experience factor that you have to figure out, hey, what do I want to do? And then you have to check it at light load to make sure that your heavily crowned piece that runs great at 80% load still has some tooth in contact when it's running at 40% load.
Thank you.
Now you know why I love spur gears, I like helical gears, and I tolerate bevel gears.
Thank you, gentlemen. Next question comes from a reader. In bevel gearing, the expression hunting tooth is often used. What is the hunting tooth, and does it also apply to cylindrical gears?
We need the whiteboard. I'm just kidding.
I'm not a whiteboard guy. Hunting teeth means, simple example, you have a pinion with 5 teeth and you have a ring gear with 25 teeth. And if you want to lap this gear set, lapping operation will work perfectly, but take into account that always the same pair of teeth will come into contact. This means teeth number 1 will have of the pinion will have contact with teeth number 1, number 6, number 11, and so forth. And if you take it out of the lapping machine and you put it to assembly, you need to be careful. If you don't put it properly together with the correct teeth into the correct slot, your lapping process is probably scrap. So what we try to do is we try to have number of teeth which don't have a common divisor. This means if you have 5 teeth on the pinion, you should take 24 or 23 on the ring gear or whatever, so that every tooth comes with every gap into contact. This is for lapping. But it's also for face hobbing approaches. If you have a common divisor in between the number of starts of the cutter head and the number of teeth on your workpiece, always the same blade will come into contact with the same gap. What you see at the end, you see exactly the precision of your cutter head in your spacing readings. If you have 13 starts, and this is why most of the face hobbing cutter heads have a prime number as starts, it's basically the best condition. If you would have a 5-inch start and a 10 teeth pinion, you see you will not be able to have a spacing quality better than DIN 6, DIN 7, DIN 8, just because of the precision of the cutter. Otherwise, if every blade goes through every slot, you have a perfect spacing quality.
Hunting tooth also applies to parallel shaft gears. There is a difference, though, if you're doing it for a different reason. People used to think that hunting tooth gears were quieter than non-hunting tooth gears. And that might have been the case for through-hardened gears. With carburizing ground tooth gears, I don't think it makes a difference.
And I would strongly second that. In the quote old days, people would always insist on hunting tooth gears, because if you had a problem with one tooth and you needed to wear it down by meshing with all the other teeth, with a hunting tooth, all the teeth will come in contact. Whereas, as was explained earlier, if you do not have a hunting tooth, in other words, a common factor, number of pinion teeth, number of gear teeth, are both divisible by the same number, that defect on the gear tooth will always mesh with the same pinion tooth, causing it to become defective and go on from there. If you do a literature search, you will find passionate discussions on why things should have hunting teeth or why things should not have hunting teeth. And I think today with carburized, hardened, and ground cylindrical gears, it's really less of a problem. And, people don't get so terrified when you design a gear set that's precisely 4-to-1.
Thank you, gentlemen. Are there any questions from the audience? Just raise your hand. Next one is from a reader. What are the advantages of asymmetric gears?
I pass.
I try to answer it. The specialist is in the back, but generally you have sometimes applications where you have only one direction of the torque. And then you can optimize each flank for its purpose. So you can optimize the running flank for the purpose of carrying the load and having a high flank capability of load, and optimizing the back flank, the other flank, carrying the stresses in the material. So you can optimize the root shape in both sides independently and use the space you have in gap to let in the tooth from the other gear optimally, and you can get some percentages of extra load only for gears running in one main direction.
This is also known in bevel gears, not just in hypoids, but if you have, for example, a ship drive, a thruster drive, it can only run into one direction, and then you can use a different pressure angle for the drive side than for the coast side. And this means if you increase the pressure angle, you have less crowning, and less crowning means that your Hertzian ellipse has more space to grow into the direction of the short axis, and this means you can increase your flank capacity. without losing load carrying capacity related to tooth breakage.
Very good. I have a comment from the audience.
Thank you for answering, first of all. I just want to add a couple points. First of all, design objective of asymmetric tooth gears for unidirectional gear drives is to improve performance of drive flanks at the expense of performance of the cost flanks, which are not used at all. They are unloaded or loaded for a short period of time. Now, the second thing, we have to be careful here. It's not about direction. It's about transmission direction, torque direction. For example, if we have a lifting system and gravity is in one direction, no matter it goes up or down, you have one flank load. Other example, we have, say, aircraft engine, turboprop engine. After landing, they shut off the engine and we stop transmission load from the engine to the prop, but prop is moving by inertia. So direction of rotation is the same, but torque is changed. So length of teeth would be different. So that is something we have to keep in mind. Thank you.
Thank you, gentlemen. I have a reader who has a question about worm gears. He says, I buy worms and worm gears from different vendors, and due to the profile definition, ZI, ZA, ZN, ZK, ZH, can I always expect that the worm and worm gear will mesh without problems?
No. A worm gear. These worm gears look from the first point of view very similar, but they are slightly different. This depends on how you machine the worm itself. If you have a ZI worm, then you have a straight grinding wheel, a very flat grinding wheel, and you produce exactly a worm which will create afterwards an involute profile on the worm gear. And this has the big advantage that you have a certain insensitivity to axis distance. If you use a conical grinding wheel or a conical cutter, you get a slightly different profile. And in all cases, at least in a mathematical case, it will not mesh with the other worm gear. And the ZA and the ZN, these are also trapezoidal flank forms, but they differ in the angle of inclination, how you put the tool on it. So be careful. ZI only works with ZI, ZA only with ZA, and so forth.
As I understand the question, it was matching the same flank type from different manufacturers.
No.
Is that right?
Not necessarily.
So I understand. If the question was, can I match one ZI from one manufacturer, one worm with a worm wheel from another manufacturer? This theoretically works. So the macro geometry is the same. It has to be matched. So either by measurement and a calculation program, which is capable of calculating the tooth contact pattern, or by matching the gears actually, but only ZI does not make sure that the contact pattern is exactly what you are looking for. So you have to combine ZI with the exact microgeometry.
Maybe after a day running, yes, the contact pattern will be there.
Thank you.
I would not recommend you buy the worm from somebody else and the wheel from a second person. It's not a good idea.
Yes.
You might save $1, but you might buy one heck of a headache.
Very good. Next question is, if a hobbed pinion has undercut, can I make it on a 5-axis machine and eliminate the undercut and optimize the root fillet?
Yes, you can do it, but you could also exhibit it on a show like this, but you will never bring it into mesh with the mating other gear. The undercut is something that is not because we face hop. The undercut is something that is kinematically necessary to bring the teeth into mesh. You need the space. If you have a low number of teeth on the pinion, you need to have the space in the root so that the tip of the mating pair will go through. Otherwise, you will have collision and interference. So it's not something that is because we make old-fashioned machines. It's a kinematic necessity.
And the other consideration is your rating practice has assumed that that undercut is present. And now you've come in with a trochoidal involute shape in the root of the tooth that isn't trochoidal involute anymore. So now you don't know what your strength rating is. You don't know what your bending capacity is. So, as was said earlier, the tooth has to not only come into mesh, it's also got to get out of mesh to make room for the next tooth. So trying to eliminate undercut by machining is saying you're not having the gear geometry that the rating standards are assuming that you're getting. And that'd be another disadvantage of doing that.
I think undercut, there are two ways of undercut. One is just a trochoid of the root shape, which you need to engage with the counter teeth. And the second one, which probably is addressed here, is cutting away active length. So when the involute goes down to the root circle, there's a limit. And if you want to exceed the limit, you can't. You will cut involute away, which is a problem that the cutter is too long. And the only way to use this cutter is to pull it out or to have undercut. Of course, with a 5-axis design, you can design whatever you like, but you will never get the involute below the base circle. This is answer 1A, and answer 1B is if you want to get rid of undercut, you can do it with hobbing also, just using the right geometry of the cutter.
Thank you, gentlemen. In some articles, tooth profiles with S-curves are promoted as more durable. Is this true? And why are those profiles not applied more often?
S-curves. That's an interesting concept. I haven't heard it referred to like that, but basically, I believe the questioner is asking about an appropriate amount of tip relief and an appropriate amount of root relief. You want tip relief to make sure you don't have tip-to-root interference. You want to have tip relief to make sure that you have low noise. And it is based on the requirement of knowing what your loads are. If you don't know what your loads are, you don't know how far the tooth's going to deflect, and therefore you don't know how to put what the, quote, optimal amount of S-shaped tooth relief on, because you can't predict where that tooth is, and a lot of technical papers been published, and yes, we can get this very quiet gear, but it's always at this one load. And if you have a varying load application, you're sort of out of luck. And I think that's part of the reason why it hasn't been used more extensively in the industry. And the other thing is you need CNC controlled equipment to do it. Trying to do it on a manual machine, you're just not going to be able to get the tooth shape.
I would like to add something. I think this refers to the S-shape where the line of action is not a straight line like involute gears, but has a straight line in the middle and some curvatures at the end. When you calculate that, you are very, very close to involute with tip crowning and root crowning. So it's more or less academic question. If you have a conjugate gear without any modification, there is a difference between S-shape and a normal involute. If you have a heavy loaded gear with an appropriate modification, tip relief and other modification like crowning, you will not have an involute shape of the line of action anyway. This will change due to deflections and modifications. So we are in the area of a couple of microns. So it's not really this relevant. A good profile modification on an involute gear gives the same result as S-shape.
I have also seen a bevel gear set. It's called the cosine bevel gear set, and the tooth lengthwise curvature, tooth lengthwise line was like an S. And when I saw this first, I thought this is a nice and fancy design. You have two contact patterns, and it will center itself by itself, so you don't need to have some axial forces on the pinion. But we took a detailed look on it and we analyzed it, and the problem is with this S-shaped tooth lengthwise curvature is that you have a dramatic load concentration on the two spots where you have your contact pattern. And this dramatic load concentration pitting capacity. And on the other side, the root bending stress is also phenomenal because the root is very, very stiff where you have the middle of the teeth, and at the end the bending capacity at the root is very low. And what will happen is you will get cracks at the end because it's in the middle too stiff. And I am very sure that you can improve, that you can take a regular spiral gear set and be by far more have a higher load capacity than this so-called cosine bevel gear. I think it's nice looking, but I have never seen it running in practice, and I'm afraid I know the reasons. There is no load carrying capacity increase.
The first time I saw S-curves was in a paper that was written by Hans Sig, presented at AGMA in either the late 50s or early 60s. And he had some S-curves on his corrections, mainly because they were running fast and they would overheat. And when the gear is heated, they distorted that, screwed up his contact pattern. So that's why he was doing that. I've never done it. I don't know anybody else who has. But Hans did. Hans Sig was that mug.
Thank you, gentlemen. I've got one more question from a reader, and that is, do the addendum modification coefficients affect the pitch circle diameter or only the outside diameter?
I'd like to answer that one. Number one, there's many pitch diameters. The reference pitch diameter is fixed. It doesn't change no matter what you do to the profile shift. Now, there's an operating pitch diameter, and that's a function of the center distance. If you're on a standard center distance and you've got a great big correction in the pinion, the operating pitch diameter is still the same as the standard pitch diameter. But when you start playing with profile shifts, you do in fact change the outside diameters of both your parts. Incidentally, there's something else that doesn't change. The base circle diameter is also fixed.
Yeah.
No matter what you do to those teeth, the base circle diameter is still the base circle diameter. That cost me a dinner when I was a very young co-op. I remember that dinner. He ate a steak.
Thank you, gentlemen. Are there any other questions from the audience? Thank you very much, then. This will conclude our session of Ask the Expert for today. We have another session this afternoon, 2 o'clock, and you can ask anything. Thanks for attending.
Thank you.
Thank you. Guys, don't go anywhere just yet. I got something for you.
Acoustics could be optimized.
Well, yeah.
The moon noise is not good.
Well,
to the bar and everybody stopped and stared. All the hippie punks cleared out at once and